So here we can take n-dimensional space. So here we are supposed to represent geometrical representation for signal for n-dimensional space. So in general, a basis functions can define using the following formulas. We are taking as gi of t equal to si of t minus summation j equal to 1 to I minus 1 Sij minus phi j of t, where we will get gi of t is nothing but intermediate functions, si of t the energy signal which we are transmitting. So here you will get Sij, that is the scalar coefficients. Phi j of t you will get as a orthogonal basis functions. So we can say you will get the coefficients we can define as Si of j equal to 0 to 2 integration Si of t phi j of t dt, where j equal to 1 to up to I minus 1. That equation already we have seen. So we can say for the special case when we are taking I equal to 1, you will get gi of t will reduces directly to Si of t. You will get directly gi of t equal to Si of t because the whole summations will become 0 if we are taking I equal to 1. For the general case, when we are taking the intermediate gi of t, the given functions we can define as the set of basis functions, so which will form a orthogonal set. You will get as phi of t equal to gi of t upon square root of 0 to t gi square t dt. That equation we have seen here. You will get, you can observe here equation 5.23. You will get when we are studying about the Gram-Schmidt organization. We are defining the second order basis functions in the form of intermediate functions. So you will get as phi I of t equal to gi of t upon square root of 0 to t integration gi square t dt, where we are taking I equal to 1 to up to n. So here now we can move to our next topic, that is nothing but conversion of continuous Avogadro wide Gaussian noise channel into a vector channel. So here we can consider the signal as Si of t. So suppose that Si of t is not any signal, but it is specifically the signal at receiver side. So we can say that is the signal, Si of t is the transmitted signal. So we can consider here Si of t is not any signal, but specifically we are considering that as a signal at the receiver side. So we can define in accordance with the AWGN. Accordance with the AWGN channel. So here you will get X of t, that is the signal, received signal. You will get as Si of t plus Wt, because here we are saying we will get the signal, that is you will get as transmitted signal plus wide Gaussian noise process of zero mean. So we can take that as a Wt, AWGN noise. You can take Wt. So we can say here the I value is in between 1 to mm, and time you can take as 0 to t. So we can take here the output of correlator can be defined as, you will get as xi equal to integration 0 to t xt phi j of t dt. So we will get here xi equal to sij plus wi. Wi is nothing but we are saying as a AWGN Gaussian noise of zero mean, and Sij is nothing but scalar coefficient. So here you can say you will get Sij, that will be equal to integration 0 to t sit phi j of t dt. And for wi, what we can write? We can write integration 0 to t wt phi of t dt. We can see here. You will see here. So here, when we are taking the Sij, that is nothing but scalar coefficient. We can take that as these concepts we have already seen when we are studying geometric representation of signal. We can take scalar coefficient Sij equal to 0 to t integration Si of t phi of t dt. So here we can say you will get that as a deterministic quantity which will be contributed by the transmitted signal Si of t, and we will get the white noise, that is AWGN with a zero mean. So you will get Wi, that is equal to integration 0 to t Wt phi of t dt. This is the random quantity. We are taking here the sample value of variable Wi due to noise, So here we can say, if we are considering now as a random process we can take as x1 of t, x of t. So if we are considering a random process x dash of t with x dash of t, a sample functions which is related to the received signal x of t as follows. So you will get x dash of t equal to x of t minus summation j equal to 1 to n xj phi I of t. So we can say here, if we are taking our above equations, we are writing the value of xj and phi j of t here. Our equation will become x dash of t equal to x of t minus summation j equal to 1 to n Sij plus wj into phi j of t. So here if you solve, you will get x dash of t equal to w dash of t. So we can say directly the value of sample function will depend only on the noise. Which noise? The channel noise. Because here if you see, you will get the sample function x dash of t will equal to w dash of t. So we can say the sample function x dash of t will depends on the channel noise. So we can say here the received signal can be expressed as, you will get x of t equal to summation j equal to 1 to n xj phi I of t in plus x dash of t. So if we are solving these, we will get equation after simplification like summation j equal to 1 to n xj phi I of t plus x dash of t को हम क्या लिख सकते हैं? We are getting that will depend only on the channel noise. So we can write x dash of t instead, we can write as a w dash of t. So we can say this is the expansion similar which we will get in equation 5.5, but it is random due to additive noise. Now we will see the equation 5.5. So you can see here, when we have seen the geometric representation of signal. At that time also, what we are writing? We are writing energy signal equal to summation j equal to 1 to n scalar coefficient into the orthogonal basis function. So we will get here also the same equations. So here we have get that equations, but it is random due to the additive noise, because here we will get x of t equal to summation j equal to 1 to n xj phi of t plus w dash of t. Now we are supposed to study about the statistical characterization. So if we are taking the received signal, output of correlated is a random signal. Now we can see the diagram, then you will get. So here you can see synthesizer for generating signal S of t and the analyzer for generating the set of vector Sj of t. So this diagram you will require here. You are using that as a analyzer here. So if we are considering here the received signal at the analyzer is a random signal Sj of t. To describe it, we need to use the statistical methods, where we are supposed to study the mathematical terms like mean and variance. So here we will supposed to consider some assumptions. These assumptions are: x of t will denote a random process. It will denote a random process, a sample function of which we are representing by the received signal x of t. And here x of t will denote a random variable. Xj of t, not x of t, xj of t. Xj of t will denote the random variable whose sample values we are taking by correlator output xj of t, where j we are taking from 1 to n. You can take j, you can take I, no matter, but only you are supposed to understand which we are taking as a random process, which we are taking as a random variable. These things we have seen in our third unit. So here we are considering x of t will denote a random process and a sample function of which we are representing by the received signal xj, received signal x of t. So here we are denoting xj of t as a random variable whose sample value is represented by the correlator output xj of t, where j equal to 1 to up to n. So we can assume that AWGN, white Gaussian noise, mean equal to 0. So we are assuming AWGN, so the noise is Gaussian. So we can say x of t is a Gaussian process and it will bring a random variable. So we can take here xj will be described by its mean and its variance. So how we are taking the mean and variance, this concept we have seen in our third unit, the random process, the mathematical parameters, mean, variance, covariance, autocorrelations, cross correlations, this concept we have seen. So here when we are supposed to talk about the statistical representation of the signal at that time, we are supposed to see its mean value. So here if we are taking x of t as the random process and xj as the random variable, we can say wj will denote a random variable. At that time it will represented by its sampled value wj. Small wj is a sample value, capital W suffix j will denote a random variable. So it will represent by its sample value small wj, which will produced by jth correlator in the response to Gaussian noise component. So it has 0 mean. Then the mean of xj will depends only on Sij. So here you can take mu of xi equal to E of xj. That is nothing but the mean. We are taking mean of xj will depend only on Sij, scalar coefficient. So if we are writing xj equal to, we have seen, you will get that will depend on the scalar coefficient and the white noise. That is the AWGN noise with 0 mean. So you will get here E of xjk, instead we can write Sij plus wj. Now we are taking Sij outside as a constant. So we can take E of wj. So if we are saying here, you will get E of wj equal to 0. You can directly equate mu xi equal to Sij. So here you can say it will only depend on the value of mean, only depend on the scalar coefficient. Now we are supposed to see about the variance. We are denoting variance by sigma. So here when we are taking Wi, white noise, Gaussian white noise with 0 mean, Wi equal to, we are taking integration 0 to t wt phi of t dt. So here we will get that equations. Now what we can do, we are taking variance that of a random process xi. So we can take variance sigma xi square equal to variance xj, because here we are taking the random variable as a xj. So you will get E of xj, instead we can write xi minus Sij square. So you will get that equal to EWJ square. So here we can say the value of variance is depend on the mean of AWGN with zero mean. With zero mean. So here you will get sigma xi square equal to E in bracket integration 0 to t wt phi j of t dt into integration 0 to t wu phi j of u du. So if you solve, you will get the value of variance will depend on the autocorrelation functions of the noise process, because if you see, you will get equation like equation 5.38. You will get sigma xi square equal to E into in bracket 0 to t integration 0 to t integration phi j of t phi I of u RW autocorrelations of t comma u dt du. So we can say it will depend on the autocorrelation function of the noise process. So here we can say the value of autocorrelation can be expressed as, because noise is stationary and with a constant power spectral density, we can express autocorrelation as RW of t comma u equal to n naught upon 2 del of t minus u. So after substitutions, we will get the variance equation as, if we are putting the value of autocorrelations R W of t comma u as equation 5.39 in equation 5.38. If we are putting the value of autocorrelations, our equation will become, variance का equation क्या हो जाएगा, sigma xi square equal to n naught upon 2 into integration 0 to t phi of t phi j of u del of t minus u dt du. So you will get that equal to n naught upon 2 integration 0 to t phi square of t phi j square of t dt. So here we can say phi j of t has unit energy for the variance. So we will finally have phi xi of square equal to n naught upon 2 for all j, and we can say the correlated output denoted by xj will have variance equal to the power spectral density n naught upon 2 of the noise process wt. Now we can see here the properties without any proof. So here we can say xj are mutually uncorrelated, xj are statistically independent. When we are supposed to see about the statistical characterization, we have seen mathematical parameters like its mean and the variance. Now we can say some properties for that. So here xj are mutually uncorrelated, xj are statistically independent. So it will follows from above, because we will get here xj as a Gaussian. So we can say for the memoryless channel, we will get the following equations. These will be true. So here you will get f x of x by mi equal to summation j equal to 1 to n f x I in bracket xj by mi, where I equal to 1 to up to m. So here when we are defining a vector x of n random variable, so we can take the random variable x1, x2 up to xn, whose elements are independent Gaussian with the mean value Sij. So we can say the output of correlated deterministic part of the signal defined by signal transmitted, and variance equal to n naught by 2. The output of correlator and the random part calculated noise added by the channel. So we will get here the signals random variable x1, x2 up to xn. Elements of x are statistically independent. So we can express the conditional probability of x that can be given as Si of t, the density functions fx of its individual element. So we can say we can express the conditional probability of x as a product of conditional density function fx of its individual element fxj. So here this is equal to finding the expression of the probability of received signal given a specific symbol was sent, and we are assuming memoryless channel. So here we can say we will get fx of x by mi equal to summation j equal to 1 to n fxj of xj of mi, where we are taking vector x and scalar xj are the sample values of random vector x and the random variable xj. So here we can say vector x and scalar xj are the sample of the random vector xi and the random variable xj. So we are taking here vector x is called as the observation vector and scalar xj we can call as the observable element. So here you will get each xj is Gaussian with mean sj and variance we are taking as n0 upon 2. So you will get f of xj x by mi equal to in bracket pi n0 raised to minus n by 2 e to the power minus 1 by n0 xj minus sij square, where we are taking I equal to 1 to m and j equal to 1 to n. So if we are substituting our previous equation 5.44 into 5.45, you will get into equation 5.45. So you will get equation as 5.46. So you can say you will get fx of x by mi equal to pi n0 raised to minus n by 2 e to the power minus 1 by n0 summation. We can take xj minus sij square को हम क्या लिख सकते हैं? We can write summation j equal to 1 to n xj minus sij square. So here if we are going back to the formulation of the received signal through the AWGN channel, we will get x of t that will depend as the vector that we have constructed fully defines, and it will depend only on the projection of the noise onto the basis function. So we will get x of t equal to summation j equal to 1 to n x I of t 5 I of t minus w dash of t. So we can say that is the projection of noise onto the basis function of the signal set that will affect the significant statistics of the detection problem. Finally, we can say the AWGN channel is equivalent to the n-dimensional vector channel, which we are describing by the observation vector, and you will get x equal to si plus w. So it will depend only on n-dimensional vector channel. So you will get that is as a transmitted energy signal and the AWGN noise with the zero mean. So you will get x equal to si plus w. Remaining we will see in the next class. Thank you.